First of all, what is a module? A module is a generalization of a vector space. So zeroth of all, what is a vector space? A vector space is simply put an abelian group, so a set with an addition operation that is commutative, and there are more requirements, more axioms, but let me just simplify it like that. So it's an abelian group with a scalar multiplication by a field. So there's a field such as the real numbers that you can scale your elements of your group, your vectors, by those real numbers. So for example, the reals over the reals, that's a vector space. The Euclidean space over the reals, that is another vector space, and so on, because you can scale the vectors by real numbers. So what's a module? A module is another abelian group, so another set with an addition, and a scalar multiplication, but now we relax that scalars to not be a field, but just be any rank with a 1. And then it has to be that scalar multiplication has to be associative and distributive and so on, but it's just basically an abelian group that you can scale by a rank. For example, the integers, that could be your abelian group, and you can scale integers by multiplying by other integers. So the integers over the integers, that's a module over Z. That's an example of a module, and that's sort of the prototype of a module. Now take 2 by 2 matrices with integer coefficients, and now we're going to scale by the integers by multiplying by the identity matrix times n. That's our scaling of matrices, and that also becomes a module over the integers. Now, if you have any abelian group G, then that is a module over the integers, because if I have any little element G in my group, I can compute G and 2G and 3G and integer multiples of G just by adding G to itself. So any abelian group is a module over the integers. And in fact, any module over the integers is just an abelian group. And that turns out to be very important, because when we prove the structure theorem of modules over PIDs, that applies to modules over the integers, because the integers are a PID, and then that applies to all of abelian groups. And that's how you classify, for example, all of the structure of finitely generated abelian groups, or how you end up classifying, for example, finite abelian groups.